All right. First and foremost, thank you everyone for coming along, especially at this time of night. It's exciting to get to talk about some of this work. So I'm happy to be here. By way of introduction, so my name is Will Troiani. I'm a PhD student from the mathematics department at the University of Melbourne. My supervisor is Daniel Murfet, who is one of the lecturers here at the University of Melbourne. And what I'm going to be presenting today is some work that Dan and I have done together over this difficult, tumultuous year that we've all had. The title of a paper that is currently going through the rounds of publication, so hopefully we'll actually get a publication by 2022, but who knows when, is titled The Gentzen-Zucker Duality, right? Now, it has relationships to some of the other famous connections between formal logic and theory of computation, and those are described down here in this kind of triangle of systems that are capable of computation, which I've written down here. And some of you might be familiar with the so-called Curry-Howard correspondence, which draws a tight connection between the natural deduction system and the Lambda calculus. Well, basically what happened with this work is at some point, Dan and I sat down and we thought, why is it that the natural deduction system was used over the sequent calculus, pardon me? And so we essentially tried to establish a connection between the sequent calculus and the Lambda calculus, which is similar in spirit to the Curry-Howard correspondence. And as we explored that idea, we came up with the work which I'm going to be talking about today. So the work that we did mostly relates to the theoretical underpinnings of Haskell, more so than the practical side of it. So I will be talking about things like lambda calculus and type theory, and et cetera, et cetera. That's what the core of this work was. Okay, and the main goal for today is to just give some guidance on how to read this paper, because there's a few points in it which are maybe not clearly the subtle parts or not clearly the points to pay attention to. And I'm hoping that by the end of today, you feel like you have a rough idea of what the work is about. And if you wanted to get some more details on the paper, you'd feel confident diving into it and giving it a read. Okay, so to give some motivation for why you would consider a system such as the sequent calculus, if you already had familiarity with the lambda calculus, is somewhat described by this slide. So I'll say first and foremost, the two systems that are capable of computation, which I'm going to be talking about today, heavily are going to be the lambda calculus and the sequent calculus. If you're not familiar with any of these systems and everything that I've said so far means absolutely nothing to you, don't worry whatsoever. I'm going to go through all of it. But what I want you to understand from this slide at this point is what is written in blue up here is a very, very basic fundamental calculation or maybe I should say computation, which is performed in the system of the simply typed lambda calculus, right? So this is a very, very basic step in the beta reduction. We can think of this as a program, and we can think of this as an input. And if this is the program which upon input x returns x, then if I give such a program a y, that ought to give me back the y, right? So that's very simple. Now, if we were to look at the corresponding computation which gets performed using the sequent calculus, then you get this big, large mess, right? As I've already said, I don't expect anyone to possibly be able to read this at the moment, although it's great if you can. But what I do want you to observe is just how this computation blows up, right? So I've written here that this computation blows up once it's translated to the sequent calculus. And so this notion of the computations being more convoluted or perhaps providing more detail in the sequent calculus than its correspondence in the lambda calculus is going to be a core theme throughout today's talk, and it's a core theme throughout the paper.
So when you say blows up, you just mean it gets much bigger, or
it just gets much bigger?
Yeah, okay. Because I originally read that as kind of fails to terminate or something like that. But
sure,
you just mean okay, cool.
We absolutely still have strong normalization and everything and confluence, everything that you expect from the Lambda calculus. The word that I'm going to be using, I won't be using blows up, is I'm actually going to be using global and local, right? So you can see, if you know what these cut elimination steps are, they're only fiddling around with rules that are local to it at each individual step, whereas the Lambda calculus is capable of performing many substitutions at once. And so we've got a local versus global notion of computation. Hopefully that clears that up.
Yeah, thanks.
No worries. Okay, so let's get everyone on the same page with the Lambda calculus. Don't strain yourself trying to read all of this. Just say to yourself, what is my familiarity with the Lambda calculus, and try to approach this slide to get the details that you are after. This is the system that I'm going to be assuming is most familiar to this audience, considering this is the Haskell group. Things to pay attention to is we are only considering the, I don't know why that's highlighting like that. Okay, let's do that. Let's not do that. Let's do that. Okay, so we are only considering an arrow constructor. So I don't have anything fancy. I'm not looking at, you know, a list type. I'm not looking at and or anything like that. So it's just nice and simple. It's just the arrow constructor. Okay, cool. And then I'm using the standard terminology. We have variables. We have a countably infinite set of variables per type. And then we also have applications, and then we also have abstractions. Okay, cool. And maybe the only other thing worth mentioning on this slide is that throughout I'll be referring to a preterm up to alpha equivalence just as a term, right? So when I say a term, I mean up to alpha equivalence. I don't mean up to beta-eta equivalence. I'll be talking about terms up to beta-eta equivalence if I want to make that explicit. And if you're unfamiliar with the alpha equivalence step, then it's written down here. But basically, this lambda x is a binding function. So it's telling you that x is now a placeholder for a potential input to the program. And so if I change the label of that placeholder, this here is substitution. You read into M and you replace all the x's with y's, then that ought to not change the actual program itself, right? Okay, cool. And so this is the, actually, before I move on, does anybody have any questions about the system of Lambda calculus I'm talking about? It's the untyped Lambda calculus in its most basic form. No questions? Okay, cool. So here's the point that I was trying to make in the previous slide. And again, this is going to be a fundamental theme. We have that computation is non-local, right? So let's consider a lambda term which might look something like this. It's some huge term, and you know, it could be a mile long, it could be 10 miles long, and we just have x's all throughout it, right? And so if I were to give that program as input, another program t as input, then all of those substitutions get made simultaneously in what is considered to be a single beta reduction step inside the system of Lambda calculus, right? Sorry, just clicked in the wrong spot there. Okay, so we see that every single substitution is taking place simultaneously, and we have beta reduction has no idea how many of those are getting made at once. Okay, cool. So this is a little bit too zoomed, or maybe that's too small. If anyone's struggling to read that, please let me know, and I'll try to zoom in. Okay, so the other system of that's capable of computation that we'll be looking at is the Intuitionistic sequent calculus, right? Okay, now this is an important slide. So let's make sure that we know how to read what's going on here. Possibly the simplest way of understanding this system is to not initially think of it as a system of computation, but instead think of it as a system of formal logic, right? So we have these deduction rules. And so the way that we read these deduction rules is if I can prove what's on the right of this so-called turnstile here under the hypotheses that are on the left of the turnstile, then I'm also able to prove that that same proposition on the right of the turnstile given these hypotheses that are on the left of the turnstile. Right? So the way that we would read the exchange rule is if under the hypotheses gamma and then labeled P, labeled Q, delta, I'm able to entail the proposition R then I'm also able to entail R under the same sequence of hypotheses, but with the Q and P swapped, right? So thinking about this as a proof, it means that if I give you the list of hypotheses in a different order, it doesn't matter. I'm still able to prove the same results, right? Okay, and to give another example, and this is going to be the most important rule on the list, possibly due to its insignificance, ironically, but let's have a look at the cut rule. So the cut rule is sometimes also referred to as modus ponens, although modus ponens can also sometimes mean something slightly different. But what this rule is saying here is, let's pay attention to the right branch initially. It's saying that if I'm able to entail the proposition Q, given these hypotheses amongst which includes P, then if I had a proof of P from a set of hypotheses gamma, then I can just still prove Q, but I don't need that hypothesis P anymore, as long as I have the hypotheses gamma, which allow me to prove P, right? So a way that you can think about this from the perspective of a mathematician, perhaps, if you were to try to write out a proof, is to say, if I had a proof which used a proposition P as a hypothesis, every time I appealed to that hypothesis, I could have just used this context gamma in order to prove that P from the ground, as opposed to appealing to it as a hypothesis that entire time. Okay, so that's what this rule is kind of reading. And then all of these rules together give you all of the possible deduction rules. And then what a proof looks like is a tree, so a finite rooted tree, where every node is a valid deduction rule. And so you can build these things on top of each other like Lego pieces to get a big long proof, right? Okay, there is an example on the following slide, but I'll get to that in a moment. Does anyone have any questions about this slide at this point? Because this is an important slide. I'm going to be using the system throughout the talk.
I guess I'm still a little bit confused with cut.
Would you like me to just...
Could we go through it again, just to and maybe zoom in on the...
Yeah, I think that zooming in is going to help.
Yeah, awesome.
Okay, so let's look at this as though there are three pieces to it, right? There's that piece, there's that piece, and then there's that piece. And let's break it down. So first, let's look at that piece. Now, what this turnstile means is entails, right? And so we're thinking about that as we're able to deduce this proposition Q, right? But it's under these hypotheses, which are on the left of the turnstile. So the way that we read this is, under these hypotheses, I'm able to entail Q. And the other possible point of confusion is what this X:P means, right? P is just a proposition, so it's just some hypothesis that I have. And then X is just a label. So in our system, we label our hypotheses, right, with term variables. Later, these term variables are going to be used in order to construct corresponding lambda terms. Okay, and so that's one piece. And then another piece is this one, and it's a bit easier. It's just saying, let's say that I'm able to entail the proposition P from the context gamma, right? Okay, so if I have two such proofs, then I'm also able to prove what is underneath the line, which is saying that I can entail Q under the hypotheses gamma delta theta, right? Because I know that under delta and theta and P, I'm able to entail Q. And so therefore, if I didn't have P, but I did have gamma from which I can get P, then I would still be able to get Q.
And so the gamma, comma, delta, comma, theta, that's kind of like gluing all those.
Yes. So
I guess I call them context. I'm used to calling those contexts, but yes. That might not be right here.
It's absolutely correct. So yeah, we can call that a context here. And so our contexts are going to be sequences of named propositions, right?
Yep.
So a gamma is a whole bunch of these guys, these like X of type P's, right? So gamma might look like X1 of type P1, comma X2 of type P2, et cetera, right? It's going to be some sequence. And then when I write gamma, comma, delta, that's just lazy notation for the sequence obtained by appending delta to gamma.
Awesome.
Does that make sense?
So I assume what makes this a sequent calculus rather than just any other type of logic is the fact that there's a sequence to those contexts. Is that?
Oh, perhaps the words are getting confused. So there's a sequent, and then there's sequence.
Yeah.
Right? Yeah. So a sequence. Sorry, do you want to jump in?
What makes this the sequent calculus rather than any other logic system?
Yeah. Okay, good question. It's because we're dealing with sequence, right? So this entails then is not there in every logic, right? So if you were to look at natural deduction, then you have to read the entire proof in order to come down to the thing that you're entailing, right?
Yep.
But here I'm listing all of the hypotheses and then the conclusion that we get at the end together in just a list. We call that a sequence.
Okay.
Okay, that'll...
So it's kind of like the way that you call lambda calculus is named after the lambda that's in it. It's not really a descriptive name.
Okay.
Here, sequent names the construct where you've got stuff on the left of it and then a turnstile and then stuff on the right of it. That's called a sequent. That's all. That's why it's called the sequent calculus.
That's a really good answer. Yes. And so I've got this table here. Yes.
Oh, I was just going to ask that kind of difference between the sequent calculus and natural deduction, is that kind of what grants this kind of local attribute to it as opposed to the natural deduction doing it globally?
Yes, that's a really good observation. So that's absolutely correct. And one way that you can actually realize that is you can just say we do have the Curry-Howard correspondence itself, right, which connects the natural deduction to the lambda calculus. So if you're more comfortable with the natural deduction, every single time I say lambda calculus today, you can just take natural deduction instead via the Curry-Howard correspondence, right? And so when I'm sitting here saying that the sequent calculus is local and then the lambda calculus is global, that's going to hold true for the natural deduction as well. And you can see that in the so-called detour elimination steps for the natural deduction. Okay, cool. And so there's a whole bunch of these rules. One last point, which is a technical point, is that the trees of a whole bunch of these different rules put together is technically speaking a pre-proof, right? And then a proof is going to be a suitable equivalence class of these trees, and the equivalence relations that we take are a fundamental part of the paper that Dan and I were working on, right? And so the equivalence relations turn out to be exactly the ones that you need in order to get a duality between this system and the lambda calculus. But we also go through the rules and argue for the equivalence relations purely from the perspective of a logician, not just trying to set up this duality that we ended up with. So I'll be talking about these equivalence relations as we go, right? So you shouldn't necessarily understand them yet. But I will conflate the word pre-proof and proof. If that causes confusion, please let me know. I'm happy to explain. Okay, let's move on. So here is an example of a proof. So you can see that we've got these axiom rules at the top, and then we can use these left introduction rules to introduce implication on the left. And then we also have a single contraction. And later, I'll be explaining how this gets, how this defines a lambda term for you. But take my word for it now, this translates to the familiar church numeral 2. Okay, cool. So the computational dynamics of the sequent calculus come from the cut elimination and normalization of cut-free proofs. So for every single proof that has a cut inside it, there is going to be an equivalent proof which does not make use of the cut rule at all. And more than just there exists a proof that doesn't use the cut rule, there's actually going to be a procedure which removes all of these cuts step by step. And that procedure of the cut removal is exactly the computational dynamics of the sequent calculus. And then there's also normalization of cut-free proofs. So you can have two equivalent proofs that are both cut-free. And in this paper, we also talk about the process that relates these two cut-free non-equal pre-proofs.
Is it the final sequent there that translates to the church numeral 2, or is it the whole proof?
It's the whole proof, interestingly. So it's the whole equivalence class of proofs, right? So you might be used to seeing the Curry-Howard correspondence, which I believe just takes the deduction. But no, here it's the entire proof. That's the way that you read the proof is it's going to be the construction of that lambda term, right? So the way that you get that lambda term is you read the final line, but the entirety of the proof is giving you the entire construction of that term.
Right.
Okay. Okay, so let's have a look at some of these equivalence relations that I was talking about. These are the so-called commuting relations. So some of the equivalence relations are simpler than others, and there's actually a family of them. So in the same way in the Lambda Calculus, you have alpha, beta, eta equivalents. We have a whole bunch in our paper, and they're not created equal. Some of them are much more simple to understand than others. So this one's not so offensive, in my opinion. That's why I've put this one first. Let's have a look at, say 2.15 here. Okay, can I highlight all of it? All right, let's have a look at this. So on the left-hand side, you can see that we exchange both the proposition P and Q, and then in between gamma prime and gamma double prime, we just weaken in another hypothesis S, right? Now, you can just see that it doesn't make a significant difference to the reasoning of this proof if we were to have just done that weakening beforehand, because they occur at different parts of the context. So if we just left x and y as they were initially and weakened in this S, and then we did that exchange, then we define these two to be equivalent to each other under commuting equivalence. Okay? And then it's worth also saying that we take the least compatible equivalence relation that satisfies all of the generators that you're going to see today. And so what that means is that this that you're reading in the highlighted section might appear in some sub part of the pre-proof, right? And those two proofs that differ only by this sub pre-proof are still going to be equivalent to each other. Okay, great.
Is it equivalent because like the root of the proof and the leaves of the proof are the same, or?
That's a good question. I guess there's many ways you could say why they're equivalent. To give an answer that is not laced in opinion or philosophy or anything, I'd like to say that this is a fundamental equivalence generator that is required in order to establish a one-to-one correspondence between the sequent calculus and the lambda calculus. And so from that perspective, what you could say, loosely speaking, is that these two proofs don't differ in computational content, right? And so since we're reading the sequent calculus from the perspective of computational content today, we define these two to be equivalent to each other. Okay, but there are going to be equivalence relations that do significantly change the structure of the proof.
Okay, so this is something that you're setting up for stuff later on.
Yes.
Okay. Cool.
I just included this slide for you to get a feel for what these equivalence relations look like.
Could there be additional equivalence relations, or is this somehow like encompassing all of them?
Yeah, so that's a good question. We didn't concern ourselves with finding the minimal set or anything like that. We concerned ourselves with readability. So if you were to go through the proofs of the paper, you'll probably think of equivalence rules and you're like, oh, surely they have this, and you'll most likely find them in there. But we've got to keep in mind that this isn't defining the entirety of the equivalence relation, right? These are just the generators. So we take the intersection of all of the different equivalence relations that contain these rules, right? And so there might be other things in there that you don't see here, but this is a nice list of the simple ones from which the other ones follow. So the only time in my work that I've ever found equivalence relations that are not in this paper, for example, are when they become quite large. You know, you have 5, 6, or 7 deduction rules coming together, and there's no point in putting them in because they're combinations of these simpler ones. But we make no claim that this is the minimal set.
Is there like a rule of thumb that you apply to like mentally figure out if you can, if some sort of equivalence holds between?
Yeah, that's a good question. So later I'll be defining the process to translate a pre-proof into a lambda term, right? And then one really easy way of keeping in mind is if they translate to the same lambda term, right?
Yeah.
So all of these are quite simple ones, because you can see if we were to look at another example, if we were to look here, you can see that the right-hand side is never changing, right? So we're not even changing the, oh, that's a bad example. That's a bad example because that one could and does change the lambda term. Okay, let's take this one. You can see that the right-hand side, what's being entailed, is never changing, right? And so that's a good indicator that these are going to end up being equivalent to each other because the type isn't even changing. And so you're already restricted to the possible lambda terms they could be corresponding to.
Yep.
Okay, let's have a look at some of the cut elimination steps. So 2.38 is one that actually removes a cut, right? So the way that we read this is we say that if we cut a proof against just an axiom rule, then, well, computationally we can read this as that's the input to the function that's on the right, and the function on the right is in what can actually be made precise, just the identity function, and so we can just do that cut elimination, and that just corresponds to the proof pi. Okay, so that's one that actually eliminates it, but most of the time we're going to end up commuting it, and so you can see that you get rules like this one, 2.39 here, where if we look at this rule R0, we're going to say that that's a structural rule, and so the structural rules only affect what's going on the left of the turnstile. So you can see that in pi 1, the gamma has become gamma prime, but then we're cutting against this hypothesis P, right? And so since we're cutting against P, the fact that gamma changed to gamma prime is not significant to that cut. It didn't affect the variable that we're cutting against. And so we equally well might have just done that cut initially, so I'm looking at the right-hand side now, and then applied that rule R0, which fiddles with the context. Okay, great. So
you still got a cut there though. You haven't eliminated.
It's not cut there though, yeah. But the key point is that its height has either increased or decreased, depending on how you read the tree. But that's kind of the point, right? Because the proof of cut elimination is going to be a inductive proof on the heights on the height of the tree. And so what you end up doing is you say grab the topmost cut, and then I prove that I can raise it closer to the axiom rules. And so rules like 2.39 push the cut closer and closer to the axiom rules, and then rules like 2.38 eliminate them. Okay, but it's complicated because some rules do actually introduce cuts. So they don't only keep it there, they actually introduce a new one. And so we can look at rule 2.5 here. This rule actually corresponds to beta reduction. And maybe you can see that because what's going on here is we're saying, if I were to input program pi 1 into the output of whatever I plugged pi 2 into, which was pi 3, well, that's going to be the same as feeding pi 2 into pi 1 and then the result of that through the pi 3. And so this is actually one of the steps of beta reduction. This was a point where I wanted to use my pen, unfortunately. I could write down how this comes out to be the beta reduction rules, but I think that's going to get too messy if I try to do that with my pen. Maybe we can try and have a look at that after the talk if that's of interest to anybody. But you can see here that the cut has actually increased in number. So this rule increases the number of cuts, but the key point is that you can see the complexity of the variable that we're cutting against has actually decreased, right? So looking at the top rule, the top proof, we're cutting against a variable of type P implies Q, right? But then on the two cuts down on the bottom of the in the bottom proof, we can see that the first one cuts against P and the other one cuts against Q. And so if you define the complexity of a proposition to be the number of times that we have an implication inside it, then that has decreased. And so later when we're talking about cut elimination, what we're actually going to do is do a double induction, first and foremost on the complexity of the variable that we're cutting against, and then second on the sum of the heights of the two proofs that constitute the cut. Okay, cool. So that might look like it's increasing in complexity, but in fact it's decreasing in complexity. But they can actually get even worse than that. You can see that 2.42, this one increases the number of cuts and it fails to decrease the complexity of the cut. Okay, so this rule is quite nasty to deal with, but the way that we handled that was by looking at so-called active contractions. And so basically you can find all the instances where such a thing like this is going to occur, and you can put them all together using the commuting equivalence relations that I showed you before. There's necessarily going to be finitely many of them, and then you apply this rule finitely many times, and the number of cuts might explode, but it'll only go up to a finite number of times. And then what you're left with is a proof where this instance can't occur again. And so then you can run the double induction on that. Okay, that's for anybody who is interested in looking at the cut elimination proof that we have. By the way, another thing that I'll flag, our proof of cut elimination avoids the mix rule, right? So we have a genuine, authentic, give me a cut, I'll tell you what you do to it, proof inside this paper, just in case that's of interest to anyone. Okay, here's the last set of equivalence relations, which I just want to mention briefly because these ones are quite interesting. So these are part of what we called lambda equivalents. This is possibly quite nasty looking, but it becomes simpler if you kind of adopt the philosophy that left introduction is similar to the cut rule, right? So if we look at 2.34, we have a contraction followed by a left introduction. And I'm saying that left introduction is similar to cut. And so we saw on the previous slide that actually duplicated the input. It meant that we now had two pi1s, and then we can just perform the left introduction on both of them. And then the rest of everything down here, that's just kind of organizing the mess that you created so that the bottom line of both these proofs end up being the same. But most of that is just exchanges and organization. The important part is the fact that this pi1 had to be duplicated in order to be fed into these two variables of type Q that we had, whereas earlier it was only one.
Just a kind of quick question. Could there possibly be like a more terse version of this kind of syntax? Because like I'm sure like you're very familiar with it, but to me that kind of looks impenetrable.
Sure.
That's certainly the middle one.
Yeah, that's certainly fair enough. So you could suppress the exchanges if you wanted, and that could help, right? We decided not to do that because, well, for a number of reasons. Dan had some philosophical / mathematical reasons for doing so. The way I was thinking about it was simply that the system has an X in it, so let's not be lazy. Let's just go ahead and work out how to organize all of the exchanges. But when I'm reading this, I don't really read. Do I read beneath that? I do read this contraction. I read that contraction, but I don't pay a lot of attention to that X. And I don't pay a lot of attention to these contractions and the exchanges because what these contractions are doing, they're just identifying all of the duplicates that you got from these two gammas, right? So obviously you're going to have to do that at some point if you want to make an equivalence to this bottom line down here. And then these exchanges, they're just putting the two variables of the same type next to each other so that you can then do a contraction. Because if I have two variables of the same type, but they're at different points in the context, I'm not allowed to just contract them from where they are. I need to just put them next to each other. So what I'm reading here is I'm saying we had a contraction followed by a left introduction, and that turned into two left introductions and a contraction. That's exactly what happened here. So you can see we've got this contraction followed by a cut, and then that just turned into these two cuts with a with the input pi1 duplicated, and then we had this contraction. So perhaps rule 2.41 is easier for you to read, maybe not. But yes, you can just start suppressing stuff if you want to. We actually don't suppress everything anyway. What didn't we suppress? Oh, yeah. So you can concern yourself with where certain rules are allowed to occur. For example, I might only be able to do a cut against a variable which occurs at the absolute rightmost position inside the context. And some people do put that restriction on, but we haven't done that here.
Just to clarify, what does the double line?
Are you talking about this double line?
Yes.
Yeah, sorry, I should have mentioned that. That means multiple instances of this, right?
Yeah, so, I'd say,
yeah, so I've suppressed a whole bunch of them. So you can see here that these two gammas, gamma has turned into that gamma, right? But gamma might be x1, x2, x3. And so therefore gamma is x1, x2, x3, x1, x2, x3. And if I want to contract them, I'm going to have to exchange that x1 to be next to the other x1 and then contract it, whatever. So that's just a whole bunch of organizations. So we suppress that into 2 lines.
It's kind of almost like a tactic or something that you can run. Oh, sorry,
yeah.
theorem prover jargon.
So these rules actually represent an internal BHK interpretation. So the Brouwer-Hazen Kolmogorov interpretation of proofs is something that's considered in the logical community, and I've already been saying this. So you can think of a proof that P implies Q as a transformation of proofs of P into a proof of Q. And so rule 2.34 is telling you that such a transformation is going to have to be duplicated if you were to do it twice. And then rule 2.35 is telling you that what you deduced, as well as the entire proof, is not going to be necessary if you're going to apply that to a rule that has just been weakened in, right? So you can see that since we weakened in the y of type P implies Q here, it doesn't have logical data. It's just a weakened in hypothesis. Whereas over here, it was genuinely created by some of the data that we had. And so the fact that these two things are equivalent is telling you that that extra structure on the left-hand side here is insignificant.
Is there a good introduction to BHK somewhere?
That's a great question. I'm not sure if I'm going to be able to give you one off the top of my head. The first time I read about it was in Sorensen and Uzitsen's book called Lectures on the Cohen-Howard Isomorphism. And there was a few good points in there about it. And I might have some other references, but I'd have to check what I've got. I can answer that question again at the end.
Yeah, no rush. That's great, thanks.
No worries. So yeah, also as I mentioned, a theme in section 4 is that left introduction can be thought of as an internal cut. And these rules reflect what we've already seen, as I pointed out. And in fact, one of the proofs of normal form later on is going to require organizing these left introductions. And you'll find that that proof actually mimics the proof of cut elimination. So you get that nice meta relationship there. Okay, cool. Let's do some maths. So the language that we used in order to establish the Gentzen-Zucker duality was category theory, right? So we just set up 2 categories and then we proved that we had an equivalence of categories. So let me give you a quick reminder of what a category is. So a category consists of a family of objects, X, Y, Z, ... And then for each pair of objects, X, Y, we get a set of morphisms, which might be F, G, H, whatever, and they have a domain X and a codomain Y, right? So objects, and then for every pair of objects, a set of morphisms with a domain and a codomain. And then we just have a few coherence conditions, and these are rather simple. So we require composition. So if I have a setup where I have a morphism F from X to Y, and then a morphism G from Y to Z, then I just need to be able to compose these. So there must exist such a morphism G after F. So we read these from the right to the left. This says that F comes first, followed by G, and that has to be a morphism from X to Z. Okay, and then there's a few coherence conditions. You've got this associativity condition, but let's not concern ourselves with that for now. And then we also require that for every object we have a so-called identity morphism, which acts like the identity. So you can see here, the way that I'll do this section is I would say if I had any morphism F from X to Y, then I can post-compose that with the identity on Y, or I can pre-compose that with the identity on X, and I get the exact same function. I shouldn't say function, morphism. Again, the exact same morphism. Okay, and then an easy example and the canonical example is just all of the sets and then the set functions between them. So these dots are meant to represent sets, and then these arrows are morphisms from these sets, right? We've got these identity functions. This one's missing an identity function, but they should have it, and we've got all of the composites, etc. Okay, great. Let's talk about the specific category, which was the category of lambda terms. So as objects, we take all of the types, right? And then we also take this special type 1. This can be thought of at this point as a technical condition, but essentially it's so that the category is able to talk about programs of type tau and not only programs of type tau, arrow, sigma. Okay, so morphisms, if you give me two objects and they were both types, so tau to sigma, that's going to be a beta-eta equivalence class of terms of type tau, arrow, sigma. Okay, and then as I just said, there are more terms than just that. There's also the ones just of type tau, and we get those by looking at the morphisms from 1 to tau. Okay, and then there's also morphisms into 1, and all of those are just given, again, a special symbol star in order to adhere to the axioms of the category. So that's very much just a formal construct that we have there. Okay, the way that composition works is if I had two terms m and n, then all I want to do is plug them into each other, but m is of type tau to sigma, so I need to give that something of type tau first. And so what we do is we just introduce a variable. Is there a mistake on this page? Yeah, this doesn't look so good, does it? Okay, I've got x of type sigma here. I believe that's meant to be an x of type tau, because I'm going to give m x, and then that's going to give me a term of type sigma, and then I'm going to give that to n. Okay, so pardon me, this sigma here, which I struggle to highlight, that is meant to be a tau. Okay, great. And then if I didn't need to give that input, like if I just had m of type tau, then I can just do normal application. And then the other possibilities are if I compose star with just a morphism of type tau, well, yeah, that's just going to give me back the morphism m. That has to, because there's only one morphism from star to star, and so therefore it has to be the identity morphism, and so we have no choice over that. And then lastly, if we go tau into 1 and then into sigma, then all we do is we just have an abstraction. Okay, cool. So you're seeing composition, application, identity, and abstraction in the composition law of the category. Identity is nice and easy. It's just this. Corresponds to what I was saying earlier, where there's a precise sense in which that's the identity function, or identity morphism. Okay, and then lastly, I kind of lied to you. It's not just that we have one category of lambda terms, we actually have a family of such. And so what we do is we say take a sequence Q of types, and then we get a subcategory, L sub Q, where every morphism is restricted to have free variables contained in Q. Okay, so we just take as the Hom set from tau to sigma, the lambda terms of type m tau arrow sigma, such that the free variables of m are a subset of Q. Sorry, I've just noticed another thing. That shouldn't say sequence. Yeah, so this is actually a set, right? So this is one of the differences. In the category of proofs, we're going to be talking about sequences, but inside lambda terms, we don't talk about the free variable sequence, right? We just talk about the free variable set. And so Q is actually going to be a set here.
Will, I think your compositions are the wrong way around regarding how you did the diagram.
Oh, sure. Right. Yes. So here, yeah, okay, I've got my conventions confused. So here I insisted that G composed with F is telling you that F comes before G, but then I've done that exactly the opposite way around here. So yes, a couple of issues here. Just make sure that you're swapping around these two, everything that you're composing in order to get the correct convention. All right, thank you for flagging that.
Sorry, just to check my understanding, you said here that we're talking about sets of types in the Lambda calculus versus but sequences of types on the left-hand side of the turnstile in the sequent calculus.
Yes.
That's the fact that you go from going from the sequent calculus into the lambda calculus direction. The fact that you go from sequences to sets. That's because you have the exchange rules, right?
That's a good question. It's not just exchange, because we also allow duplication, right? So a valid context inside the sequent calculus is just x of type p, comma x of type p. And then, we had to make allowances for that as well.
So it's those the structural rules in particular, the contraction as well as was it now?
Yeah.
Contraction and
contraction, weakening, and exchange.
Yeah, all three. Yeah, sorry. Yeah.
Yeah, 100%. So it's common to consider the context of a sequence inside logic as just a set, but here we decided to deal with sequences, and the main differences that they give you is duplication and order, right? And so therefore, yes, exchange bears meaning. If you're dealing with a system where we're looking at a set, exchange would be meaningless. And then something like weakening, but specifically weakening a variable that was already there, also becomes a meaningful notion.
Yep. Greg Rester would approve.
Yes, I'm sure. Okay, cool.
Was there sorry, I'll not make this too long. Was there a reason to split it into like a family of category kind of correspondence? Was that just to aid with like inductively showing these properties, or was there another reason to split it into a family?
That's a good question. So initially, Dan and I were actually investigating the categorical structure of the lambda calculus, right? And so we wanted to realize abstraction categorically, and we found that we could if we considered it as an adjunction between these categories. So if you take LQ and LR, where R is a superset of Q, then when I'm mapping from LR into LQ, I need to bind some of the variables, because R has got more allowance for free variables than Q does. And so the way that you do that is you just put lambda abstractions at the front. That was where the investigation started. And then why we didn't... So there's no corresponding notion on the sequent calculus side. You can't talk about, for example, just a proof with an infinite context, right? Where you can just have whatever you want. And so the structure of a fixed context is present in the sequent calculus. So you could take the union over all of them. I think that the category theory is a bit more complicated. I think it's not quite as simple as what it sounds. I think that if you go into the details, you'd actually have to do something a little bit clever. But that's a good question. I'm not entirely sure. Okay, let's talk about the category of proofs. So yeah, here we're talking about a sequence. It's a sequence of variables, and keep in mind the variables are named here. So it's x of type p, comma, comma, dot, dot, dot. So the objects are going to be all of the propositions. Union, again, just some formal symbol 1. Now, we don't actually draw a distinction between the propositions and the types, by the way. So in the lambda calculus, you say for every single type, there is an countable infinite set of variables of that type, blah, blah, blah. You do the exact same thing for propositions inside the sequent calculus. And so that's just artificially like disidentified, right? So at this point, we just identify them. So the set of propositions is literally the same set as the set of types. You're allowed to do that. You can just let them be equal sets, and that's perfectly fine. The morphisms are just going to, from P to Q, are going to be the proofs that P implies Q inside the context gamma. Okay, great. And then a morphism from 1 to P is just a proof inside the context gamma of P. And then composition is a little bit complicated, because we need, so if we have something like this, P implies Q, you need to move the P onto the left in order for you to do a cut against it. So essentially we want cut to be given us the composition. Again, it looks like these compositions have been written with the reverse convention. That's my bad. But what we do is we say, if you give me a variable x of type P, we fix some transformation which will map a proof of gamma that a proof that in the context gamma P implies Q to one that in the context gamma and P we can entail Q. So all that's doing is moving the proposition P onto the left, such a thing exists, and we just fix it. And then we can just go ahead and use that in order to set up these two proofs, which are then able to be cut against each other. But then once you cut it, you end up with this X of type P on the left, and so you better move that over to the right. Okay, good. And then the identity proof is just going to be an axiom, and then you just weaken in all of the hypotheses that you need. Okay, good. That's it for this slide. People feeling good? Any questions at this point? All right. Yep.
The associativity and the identity rules, they come from your equivalence classes. So when you like compose a morphism with the identity, it's equal to the same morphism because of the equivalence rules that you described earlier.
Yeah, that's exactly correct. Right. So if I cut against this axiom rule, then that's going to correspond to composing with the identity inside one of these, with Q chosen appropriately, or gamma chosen appropriately. And you can see here that we just say that that's equivalent to the same thing. And so you take this and then you post-compose it with the identity, and you get that, and then these are defined to be the same by our equivalence relations. So yes, that's completely correct.
Cool.
Okay, good. So here's another important slide. So this is how you actually translate from the sequent calculus to the lambda calculus, right? All you do is you go through the deduction rules for the sequent calculus, and then you annotate the right-hand side of the turnstile with a lambda term, and then you're slowly building up a lambda term as you go. So if you look at axiom, beforehand, we didn't have this X on the right-hand side. We only had it on the left-hand side, right? But here we just introduce it, and then cut ends up being substitution. So everywhere inside M, I have this free variable X. And then if I cut against a term which I've built up, which is N, then I just replace all the X's with the N's. Makes sense? Contraction is saying that if I have two different variables of the same type and then I identify them, I better identify them inside the term as well. Weakening doesn't affect the lambda term. Exchange doesn't affect the lambda term. So this is important. This is also telling you the kind of things that sequent calculus can see that the lambda calculus can't. And this was, I don't know who asked this question, but it was exactly a point that was made earlier. Since we're dealing with sets inside the lambda term and we're dealing with sequences inside the sequent calculus, we would expect something like this. Okay, right introduction corresponds to abstraction. That one's nice and simple. Now, left introduction is perhaps not immediate, but the way that this works is we introduce on the left-hand side of the turnstile a variable of type P implies Q, right? And so what we need to do is go through the term M and find all the instances of X and replace that with our input N applied to that term Y, right? So we have Y is of type P arrow Q. If I give that an N as input, which is of type P, then I end up with something of type Q, which is exactly what X was of type. And so therefore you can go ahead and do that substitution and everything's well defined. Okay, great. An example is given down here. I'll remove the highlighting so it's easier to read, but maybe just pay attention to the right-hand side. You can see that you're slowly building up this term. So you start off with an axiom X triple prime that gets built up using the left implication to Y prime, Y double prime, X double prime, and then so on and so forth, until eventually we end up with this rule, pardon me, this rule down the bottom here. And then the lambda term that we take is Y double prime, Y, X. Okay, great. That defines a functor between these two categories. And then we have this theorem. So if gamma is, and this is one of the main theorems in the paper. If gamma is repetition-free, then the translation functor is an isomorphism of categories. And so here we've just taken Q to be the underlying set of gamma. okay, I think there's a bit of this slide that's not, yeah, here we go. Okay, so if you don't like equivalence of categories, or if you think it's like somehow loose, it's very much not, because we end up with this natural bijection of Hom sets, right? And then keep in mind that the Hom sets were the proofs and the programs. And so this is telling you that we have a bijection between the two of them. Okay, so to sketch the proof of it, the difficult part is injectivity, right? Because if I take two proofs that map to the same lambda term, I need to show that those two proofs are equivalent to each other under these equivalence relations. Again, the way that we did that is that we defined this equivalence relation, just equivalence O, which is just, it's just the largest, it's the equivalence relation that contains all of the equivalence relations that we defined in the paper, except for those that change the lambda term, right? So we don't, so in particular, these two proofs, if they're related by O, can't map to two terms which are related by necessarily using eta equivalence or necessarily using beta equivalence, but they might be alpha equivalent to each other. So what we did is we reduced down to the case where pi 1 and pi 2 are in particularly nice forms. And so this is one of the things that we defined in the paper, is this so-called L left implication normal form. And this is definition 4.17 here. So a proof pi of gamma entails p is called a left implication normal form if we have the following conditions adhered to. So first it needs to be cut-free. That's an obvious one to take. And then well-labeled. Don't worry so much about well-labeled. Well-labeled is essentially a technical point in order to ensure that the substitution inside the translation factor is behaving how you would want it to. Because, for instance, you might apply a rule that performs a substitution on an x, but your context might have had several x's which are different in meaning. So you might build up your term on the right with different types of x's, and then when you do a substitution, it will replace all of them, right? But it will only replace the one that you have in mind as long as the proof is well labeled. So well labeled is somewhat of a technical condition, but cut-free is meaningful and necessary. And then we also ask this, that no contraction is active for a variable occurrence eliminated in the left implication rule. So what's going on there is that is exactly what I was mentioning earlier, where we don't want to cut against a contraction rule so that the input gets arbitrarily duplicated. Okay, and then we also require that no variable occurrence introduced by a weakening rule is equivalent under the relation of strong ancestor. And so there you're moving up the tree in order to find what the strong ancestors of your variable are, which is eliminated by the left implication rule. Okay, I tried to think of a nice way of thinking about this set of rules, and I think probably the nicest way of thinking about it is if we just go back to these lambda equivalence relations that we gave. If we think about 2.34 as a computational step, so it makes a step from the first proof to the second proof, and then 2.35 in the same way, it's a step from the left one to the right one, then this left implication normal form is once such things are fully reduced. So you can't come up with any more instances like this. And then moreover, the proof is cut-free and it's well labeled. Okay, great. And so once we've proven that you can get down to a left implication normal form, we then proceed by induction on the structure of the term. So we're saying maybe the term is a variable, or it's a lambda abstraction, or it's a application. And so this becomes a case analysis, and we came up with normal forms for these three situations as well. Two of them are easy, one of them is hard. So lemma 4.21 tells us that there exists such a thing as a variable normal form. And it's this simple thing. So you just take an axiom and then you weaken in the hypotheses that you don't use. And then lemma 4.22 is telling you that you have the existence of an abstraction normal form, which, speaking loosely, can just be thought of as the right implication rule that introduces that lambda abstraction is the final rule. Okay, application normal form is more difficult. So this is the definition of application normal form. Again, let me know if you need me to zoom in a little bit. So I'm not going to go through this finely and analyze all of the details. I just want to give you some kind of understanding of how to read this. In fact, I will zoom in a little bit. Okay, so what you want to keep in mind is first say to yourself, why is this so complicated and why should we expect it to be so complicated? Well, for variable and abstraction, we had rules that corresponded exactly to them, right? So variables just come from axioms, and then abstractions just come from right implications. Whereas we didn't have a rule inside the sequent calculus that just gives you an application, right? And so we need to build those applications up by hand, one variable at a time. And that's what's going on here. So the way that I think about this, again, speaking somewhat loosely, is that you have this rack where you can input these programs. So this like tau b minus 1, tau 1, and zeta, these are all inputs to your rack. And then you put them all together. And when you do that, you're slowly building up your term. So you've got this x of type p at the top, that becomes yr, where r is whatever the term is corresponding to zeta. And then that y gets replaced with something more complicated, y1, l1. And then that just keeps happening. We ended up suppressing the lambda term in order to define this. So it's gone now. But you would see inside here, y b minus 1, and then l b minus 1, l b minus 2, l b minus 1, blah, blah, blah. And so you're slowly building up that term until eventually you get down to the bottom. And then by here, you will have a whole bunch of different contractions and weakenings that you have to make. LAD stands for ladder. That's just a certain type of sequence of exchanges that we defined in order to try to get them, because we're trying to attack a normal form, so we need to organize everything. So we came up with an organization for how the exchanges should be made, and they were called ladders. Okay, great. And then we asked for the following set of rules to be satisfied, or the set of conditions to be satisfied. First, we require that all of the inputs are themselves left implication normal forms. We also ask for well-orderedness again. And we have this one, no variable occurrence in gamma has more than one weak ancestor inside delta. Blah, blah, blah. This is another somewhat technical one. And the way that I think about these two rules together is they're organizing the contexts, right? So sequent calculus has more complexity than the lambda calculus in that it's constantly carrying around more than just its set of free variables, but its sequence of it as well. So you need to organize all of that. And rules 2 and 3 here are just some line in the sand that we drew to say this is how it should be done. We've got the same thing for the contractions. We organize the way that the contractions should be done. Okay, rule V is a confusing one, but basically you could have free variables inside these terms here, L1, L2. Sorry, one of my pieces of technology is talking to me. Oh, it thinks I'm talking to it. No, I'm not talking to you. Okay, sorry. So this L1 here, this R here, this LB minus, sorry, where is it? LB minus 1, they all might have free variables inside them, right? And so if I just like used different labeled free variables, then I might have a different left implication normal form. But we organize that by coming up with a canonical list at the start. So we just say, first and foremost, if you're going to use free variables of a particular type U, then they have to occur in this list, from this list in this order. Okay, great. And then these last two, just as I already kind of mentioned, they organize the weakening rules and the ladder rules, which we just push all the way down to the bottom, which we're able to do with the commuting equivalence relations. Okay, and we get uniqueness in some sense. So it's unique in the sense that if you have another one, which is of the same form with all of the same pieces, then we necessarily get we get uniqueness up to such those choices. Okay, and the proof of uniqueness is an application normal form. Yep.
I'm probably missing something, but why do you preserve the free variables rather than just dropping them?
Well, many reasons, I guess.
Sorry, yeah.
No, that's okay. I'm just trying to think of a the best way to answer the question. They're not really free variables, right? So they become free variables once we translate them over to the lambda calculus. But from the perspective of the sequent calculus, they're the left-hand side of the turnstile. They're part of the sequent, right? And so that structure is present inside the sequent calculus, and we want to order it. So what we're actually heading towards here is a normal form for sequent calculus proofs, right?
Right,
which means
right.
that is there. So the lambda term isn't going to care about all that kind of stuff, although it will in a sense. It'll care about the set of free variables, but yeah, as I've said, in the sequent calculus, we care about more than that. Okay, sorry,
that makes sense. Yeah, thank you very much.
Nice. Okay, great. So they're the normal forms that we came up with. But they're not truly unique, right? They're unique in an appropriate sense, and they get you through the proof of the theorem that I mentioned earlier, that you get the equivalence of categories. But we realized that we could do better. You can actually just organize the pre-proofs up to alpha equivalents, right? Maybe a good place to start actually is on the right-hand side of this slide. So if you look at, I can't seem to highlight it, but if you were to look at this crazy diagram that I have over on the right, what we have so far is a whole bunch of, so this is me trying to draw the category, right? So we've got all of these different propositions, or I guess these are proofs. Okay, so say we've got these different proofs, and they're all mapping to various different terms, right? Then we know that the terms have a beta-eta normal form. Like such a thing exists in the simply typed lambda calculus, right? And so wouldn't the story just be so much neater if there was a corresponding sequent calculus normal form, right? Such that all of the different things that map down to the sequent normal form, well, they themselves map to terms which also normalize down to the beta-eta normal form. And so therefore you can just concern yourself with normal forms. You can say, okay, forget all of these non-normal form ones. I'll just take the normal form of the sequent calculus term, and then I'll map that to whatever lambda term I get, and I know that that corresponds to the normal form, the beta-eta normal form for the lambda calculus. And so that's what we're heading towards now. And in fact, we found it. And so that's what theorem 4.49 is telling you. And so this is the other major theorem of the paper, right? So the way that we read this is that we can say, okay, sigma sub p sup gamma is all of the pre-proofs of the proposition P inside the context gamma, and then that N at the front of it is normal forms of such types. Sorry, normal forms of such things. And then if I take that modulo alpha equivalence, and so we have a notion of alpha equivalence corresponding to the sequent calculus as well, we should just get by looking at what it is in the lambda calculus and then mapping it over to the sequent calculus. And if we look at that up to alpha equivalence, then if we just include that into the set of all proofs, modulo proof equivalence, so we're not looking at normal forms anymore, then that we know that that already has a mapping over to all of the beta-eta equivalence classes of lambda terms. And we know that that has a corresponding set of normal forms itself. And we come up with all of these maps and all of these sets such that this diagram commutes. And so this diagram is the formal diagram of this diagram that I've drawn up here, right? So upstairs, you have all of the proofs and all of the terms, and then downstairs you have the normal ones. And you can see that the commutativity of this diagram is saying that the normal forms map to the normal forms. It's bijective, so you get unique inverse images, etc. Okay, cool. And so the last thing that I want to talk about today is what this normal form is. So we're nearly there by the time that you have the abstraction, application, and variable normal forms, but we just need to organize a couple more things. And so we came up with this concept of boundary violations. So first of all, if we look at this contraction that happens here, what might be the case is that both this x and x prime of type P, they both might occur inside this lambda, right? And so that means that that contraction couldn't just happen before that left implication, right? We call such a situation a boundary occurrence, a boundary violation of contraction type, right? And then later we're going to ask for a normal form to admit no such things. And then the other thing that we need is a boundary violation of left implication type. And what's going on here is that this left implication might be against a variable which again occurs in lambda. And so in a sense, these two left implications are the wrong way around, and we can just fix that using the commuting relations. Okay, cool. So definition 4.41 is telling us what well-structured means, and it's a very similar list to what we've already seen. So we add to this list that there are no boundary violations for contraction type or left implication type, and then a set of other rules. And these rules are such that if you look at either a variable abstraction or application normal form, and then you ask for a few more conditions, then that thing will end up being well structured. That's how these rules were discovered. Okay, but mostly it's just coming up with an order for things. So for example, rule G, we just come up with a labeling system for the so-called derived contractions. Derived contractions, again, is another way of ordering the contractions that we came up with. And we just insist that they occur in lexicographic order. So it's just organizing the proof tree. Okay, cool. And then a proof is actually normal if it looks like this, where psi is well-ordered and well-structured, and then we have these ladders and weakenings, and the ladders and weakenings occur in a fixed order. Okay, and so we have an example here. So this top proof is an abstraction normal form, but it's not normal. And the reason why is because we get a boundary violation of left implication type, because you can see this left implication is against this variable, and that variable occurs up here, which is above a second left implication rule. But that's okay, we can just swap that around. And so once we do that, we can see that we don't have such a thing, and so therefore we have no boundary violations. Then you can go through the rest of the list and check, and we do indeed get a normal form. Okay, great. That's the end of my talk. Thank you for listening. Any questions?
Wow, thanks so much.
No worries.
Excellent talk. I guess I've got a question about that very last slide.
Yeah, let me do it.
So the boundary violation, the purpose of that concept is to kind of force further normalization, is it?
Yes.
Okay.
Yeah, that's a technical way of thinking about it. You can get meta and try to philosophize about it and say that you could say that a program should be like sectioned off, right? So you've got like all of the inputs that are related to this section of the program. You can draw a box around it, and that's all one subsystem, right? And then that gets fed into another system, gets fed into another system. That's where boundary violations get their name. And so in a sense, it's organizing the coherence of all of the programs, like the sub-programs of your parent program.
Right.
It's not a way of thinking about it, but yes, it's to force the normal form.
So is there any possibility of going the other way from lambda calculus to sequent calculus?
Oh yeah, for sure. So that one's not actually as nasty as you might think. We have, I think we did write down. Yeah, I believe the paper actually does have an explicit description of how to do that. I don't have the slides here. Let me see if I can say something about it. You're essentially unwinding the lambda term, right? So if you take a lambda term, you can do a syntax tree of that lambda term, and then with a little bit of tweaking from that syntax tree, you can come up with a sequent calculus proof.
Cool.
Yep.
In terms of the kind of well-labeled requirements, was there any kind of thought put into like what that might entail, or it's just like they've got to be kind of unique? I guess I'm just thinking from the kind of perspective of like, de Brownifying or something like that.
That's a good question, and that's not something that I'm familiar with. But in terms of the well labeling, what the thing that might the point is, let me make this explicit. So let's go to rules. Okay, let's look at the cut rule, for example. So you can see that when we cut, I replaced every single x inside M with N, right? But the thing is, theta might have x inside it, right? So there might be multiple x's inside M that have come from a different place, right? Even though they're all x. And so then when I do this substitution, it's just going to go ahead and identify all of them. It's just going to make every single one of them n, no matter whether those two x's were actually related, were actually the same occurrence or not.
Yeah,
right?
yeah.
And
No,
so
that makes total
so what
sense.
you can, yeah, and so what you can do is you can go up theta. You can be like, okay, and that's where the strong and weak ancestors come from. So you go up the tree through theta, you can be like, okay, where do I find all of the different occurrences of x, and which are the ones that are related to each other via this ancestor relation, and which ones aren't? And the ones that aren't, you can change, which you're allowed to do because of alpha equivalence. And then when you do this substitution, you know that you're only doing it against the one that you actually have in mind.
Right.
Okay, does that make a bit of sense?
Yeah, absolutely. I guess I had like one final
we've got a question.
Oh yeah, sure.
Sure.
There's a question from Les saying, do you use any automated system for manipulating sequence and rules?
No. And it pains me to say that. So we absolutely need that in this community. I have been dealing with second order sequent calculus recently and system F. And if anybody knows any automated system that helps me simplify these things, I would greatly like to hear about it. However, well, the beautiful thing that I have is the iPad. Being able to highlight a section and copy it and move it around is really helpful. But no, this has all been mostly the old-fashioned way.
So there's no like sequent calculus kind of, I don't know, theorem prover kind of thing that you can use.
I'm certain such things exist, but I haven't
Yeah.
been smart with them yet. I tried to work on something similar to that a while ago, and in the end, I came up with basically a parser that takes I had this thing that took a linear lambda term and then outputted its syntax tree. And I was hoping to get that thing to start performing beta reductions, but that project never ended up happening. I'd be very curious just to know if anyone else has done such a thing, and I definitely like to.
Brendan's like fun.
Brendan, do you know if the stuff that Andre Bauer's been doing has got any, would be of any relevance here, or just other automation stuff?
Oh, do you mean the Andromeda stuff?
Yeah, or anything else he's done. It's just a name. I just know of the guy. Saw his ICFP keynote last year.
Not sure. What was the name? Could you let me know the name and I'll write it down?
Yeah, I'll make sure I spelled the first name correctly. It's Andre, but it's Slovenian, so it ends with a J. I don't remember whether there's a Z in it or not. Let me check. The surname is Bauer, like the normal German one. Let me just have a look up.
Yeah.
I put it in the chat.
Thanks.
Yeah, it does a lot of type theory and cubical type theory and all the fancy stuff.
It's definitely a name I need to look up in that case.
Yeah. And he's got a theorem prover that's kind of, I guess, I think it's agnostic on the fundamental logic or whatever you call it, foundations.
Yeah, it's specifically designed so that to let mathematicians pick which axioms or assumptions, or which axioms they want to have.
Yeah.
I had.
Yeah, he's got a video channel somewhere. Someone on the FPC Slack mentioned it. Yeah.
Yeah. There's a really cool set of different series of lectures on different theorem provers that people are working on at the moment. But I don't know if he went through Andromeda. Anyway.
I had a quick question about the kind of impact, I guess. Like earlier in the paper, you mentioned that although like the philosophical impact of Curry-Howard was enormous. The actual kind of like day-to-day impact on mathematics was not so large. Like, do you think that this kind of new equivalence is going to make it more accessible to automated theorem proving or something like that?
It's a really interesting question. I mean, I don't want to make any guesses on that. I think that it's not a published paper yet. This is just the preprint, and we'll wait to see. But one thing that I've always thought, there's an awesome quote by a mathematician. I need to work out who actually said this. But they say the interesting part of an equality is not how the two sides are the same, but it's how they're different, right? And so I've always found that I think the reason why the Curry-Howard isomorphism didn't make as many waves as you might expect in mathematics is because the systems are so similar. So you have the natural deduction and you have the lambda calculus, and they're just identical. It's like they're isomorphic. There's no equivalence relations, just doing one thing and the other. It's just different notation for the exact same thing, right? And so there's a limitation on the amount of kind of insight that the two sides could give each other. Whereas hopefully for like the Gentzen-Zucker duality, you see that there is true stuff that one of the systems can see that the other one can't. In fact, a good way to put it, I think this is a nice way of thinking about it. If you think about the functor from the sequent calculus to the lambda calculus, and you pick a particular lambda term, right? And then you look at its pre-image, right? So its pre-image is going to be some equivalence class of proofs. And then what if you look into that equivalence class, right? So look at all of the different proofs that map down to the same lambda term. Then you can ask the question, what information is inside that set of proofs? Because there's more proofs than there are lambda terms. Is it telling you anything, right? And that's where you get this local global notion of computation from. So one answer to that is if you pick two proofs that map to the same lambda term, then if you look inside the equivalence class of all of the proofs that map to the same lambda term, then inside that equivalence class is going to be a whole bunch of other proofs where this first proof maps to the second one, maps to the third one, maps to the fourth one, until you get down to the other one. And they're all doing these local computational steps, right? But they're local in a way that the lambda term can't see because they're all mapping down to the same lambda term, right? So the sequent calculus is kind of filling in the local computational steps that the lambda calculus is unable to see, right? So
it sounds akin. I have no idea whether this is actually the case, but it sounds akin to different evaluation strategies you have for various programming language implementations. So it would be neat. I don't know whether there's existing work on this. There may well be, but it would be neat if there were. You could say, call by value looks like this. Call by object reference looks like this in the sequent calculus. Call by push value, which Brendan Olsen probably knows far more about it than I do, but it seemed interesting. We're seeing we actually this smaller structural bit that subsumes call by value and call by reference and a bunch of other things. It'd be neat to see that represented as a bunch of something native to the sequent calculus.
Yeah, that's a great suggestion. Thanks for that. I do like that.
That's
very exciting. Thanks for that.
It does feel like it would have something to say with complexity theory, though, right? Because you've got more computational options. Like there's different parts of computation that lead to the same result than there are for the corresponding inside lambda calculus. So maybe there's some insight there. Be great to see.
Yeah. I have one other question, if I may. This is to go back to the thing you mentioned before about it relates to, I think, what Brendan was saying, mapping backwards, reversing the mapping, going from the lambda calculus to the sequent calculus, where you talked about, Daniel was like insistent for mathematical and philosophical reasons. No, we are going to keep the sequencing on the left-hand side of the sequence, and we're going to keep, when it's going to be multi-sets, right? If it needs to be, when we're not going to, you're going to have you have to care about contraction and weakening and exchange. Are you able to say anything about what those motivations were and how you feel about those, if you have an opinion?
Dan approaches the sequent calculus very computationally. It's not really a system of logic to him, I believe. Well, like it is, but he looks at it as a programming language. And so one discussion that he and I had on a public forum, some people might have seen this, is he was talking about when you're performing a computation, there is an order. If you were to write down your set of hypotheses, you will write one and then the other on the right of it, right? And then if you were to actually manipulate those proofs, well, on the page, there's going to be a difference between the one where you wrote hypothesis 1, then hypothesis 2, versus hypothesis 2 and then hypothesis 1. Now, it's not the case that there's a meaningful computational nor logical difference between the two of them. That's why we make them equivalent, right? But it's not to say that these are literally the same thing. And so he draws a distinction there and then starts deciding, defining equivalence relations for when they're the same. But he has some opinion that order of, maybe it's order of data to him, maybe it's order of memory to him. I'm just not entirely sure. But the order of the hypotheses that you're using is there, and its present structure, and so should be considered.
Yeah, that's an interesting thought, because I was thinking about, for example, if you, most of our computational, CPUs and the memory layouts they use, they're limited parallelism, right? The original, most of the used ones were uniprocessors. You only literally executed one instruction at a time. An interesting thought that I don't know whether this would be fruitful anyway, but one thought that occurs to me is, okay, you've got ordering of resources or your values in memory. Well, the von Neumann architecture we use, we've got linear memory addressing, although in actual physically, they're in memory banks, and so you actually are pulling data out in order. But spatial separation and spatial distribution matters for actual CPU execution. So if you wanted to get really bonkers, you can go, okay, let's try to represent in our calculi separation and ordering and grouping and something that represents how we fetch stuff out of memory, and we actually get batches that are next to one another, like however many bits wide, and pulling them in, and then all the cache interactions with all that weird sort of stuff there. So it might be interesting to flesh that out more clearly with the physical architecture.
I think that very much shows how Dan thinks about it. And yeah, of course, there's intention to extend this stuff. So as I mentioned, I've been looking at pushing this to second order. Another direction is to push this to linear logic, and then you can go further where you start looking at meaningful differences between exchange, etc.
Unfortunately, I can't remember enough of my aborted half philosophy honors with Greg Restall to say anything about the philosophical motivations for being substructural, because they're obviously he knows a lot about why you actually care about those structural rules, but he's obviously having written his first book on it. He cares about that a lot, and thinks there are good reasons for doing it, but I can't remember any of it, unfortunately.
Yeah, well, definitely be great to have a conversation with him at some point.
We might wrap up the questions, unless anyone has any last questions for the recording, because this session is being recorded, if you weren't aware of that. So any final questions?
Yeah, I had a quick one about could you comment on the title of the paper and the significance of those names?
Yeah, we found out pretty late into the paper that some of the results somewhat already existed, not quite in exactly the way that we had it. But that's what this diagram is at the start. So you could say to yourself, okay, I'm not going to draw a distinction between the natural deduction and the lambda calculus, because the Curry-Howard-Ask morphism tells you they're the same thing. That's why we have an equality down here, right? And then you might say, well, surely someone in the logic community at some point wondered what the difference is between the sequent calculus and the natural deduction is, right? And so therefore, since natural deduction is lambda calculus, you're essentially doing exactly the same thing as what we did. Indeed, people did do that. So Gentzen invented both the sequent calculus and the natural deduction, and he described a map from the sequent calculus to the natural deduction, and then Zucker analyzed its kernel in a sense, but he didn't look at exactly the same system as what Gentzen's original sequent calculus was. But it's still a significant paper and very close to our results. And then Mintz looked at coming up with normal forms of again, sequent calculus terms, but it wasn't exactly the same sequent calculus system as what Gentzen did. This was another point that we insisted on in our paper. A lot of people kind of moved away from Gentzen's original systems, but we went back to them and worked with truly what he wrote down originally. So we extend the normal form and we extend the correspondence, but such results already existed in literature. So we titled it Gentzen against Zucker. More statements about what that work is and how it relates to ours and how ours differs is in the paper as well.
I think that's a great place to leave off for a final question. So maybe we'll give a final round of applause before I stop the recording, and then we can all socialize as long as we like after that.